I will write the title of my talk. First of all, I will briefly review what is this title. Equivariant cohomology is one of the very important invariant in transformation group theory. And I often write this M. It's defined by we give some group action G action this space. Then we define this kind of a topological invariant for this space. And so it's an invariant. So we see that if two transformation groups are same, then we give also another equivalent cohomology from here. Then it's same, then it's also same. So this is invariant of the transformation groups. And usually, so if they are same, then this is same. Usually, this is not hold. This direction is not fold. But restricted to the nice manifold or nice classes, then sometimes this direction hold. And today's talk, I will explain about in a hypertoric manifold case, this direction hold. I will explain about it. So first of all, I will define a hypertoric manifold. This is one of the main objects in this talk. To define a hypertoric manifold, I need to define the hyperkähler moment map. So first of all, I will explain about it. A hyperkähler moment map is defined from the torus actions on a Cartan unique space. So first, this H will be a Cartan unique space. That is, this H is same as R4 as a vector space. So it's spanned by 1, I, J, K. These are bases of H. And from these spaces, we regard this H is same as R4. And this basis satisfies these conditions. I square, J square, K square, and IJK is -5. This calls a Cartan unique space. And Cartan unique space has S1 actions like this. This has a S1 action. S1 is a compact abelian Lie group. And you take some element from here. We denote it T. And we can denote the element of the H Cartan unique space as this, Z plus JW. This J is this J. And so you can take Z and W from the complex space. Then T acts on this space, this element, by this rule. It's just multiply from the left side, TZ plus TJW. And now from these conditions, we see that this is TZ plus T inverse W. So we see that from these actions, this H is same as this space. C plus C bar. C bar is orientation reversing. So it's coming from this part and this part. This part standardly and this part inversely. So we can regard this space as this one. And now we denote Tm as the m times product of the S1s. Then we can easily extend it to this action to the HM, Tm actions on HM by diagonally. So that is each element satisfies, each coordinate satisfies these actions. And you can take some a subgroup from here. Subgroup is also abelian subgroup, so it's also torus. And from these restricted actions, we can define these k actions. It's a restricted action. From these actions, we can define the hyperkähler moment map. Hyperkähler moment map is denoted by this character, mu hk. Hk is a hyperkähler. And this is a map from HM. HM is this space. To the first part is, we denoted this one. And next part is this one. And here, where this T star is a Lie algebra of Tm. And T star C is its a complex phi. Complexification of Lie algebra T star. And K star is also a Lie algebra of K, and K star C is its complexifications. And this, first of all, I will explain this mu. This iota is coming from the this map, this natural embedding map. Because K is a subgroup, so there is some embedding map. And from this embedding map, we can induce the Lie algebra level embedding map. And I'm sorry, dual Lie algebra of Tm. And we take its dual. Then we define this map. And this iota star C is its complex phi. And this map is defined by this one. Now ZW is an element of HM, so like this. ZW is defined by this one. And this mu CW is, I'm sorry?
There's some notation confusing. T to the M or T? T is the dual algebra, Lie algebra of Tm, right?
Dual Lie algebra. Yes.
K inclusion to T or T to the M?
K inclusion to the Tm.
Next one
is K inclusion to the Tm.
T or Tm? You said T star is the dual of the algebra of Tm.
Lie algebra of Tm. Yes, T star is dual of Lie algebra of Tm.
So it's better to write T, right? Don't you think so?
Which one?
T to the m's power.
T to this one. Okay. Yes, T. And this mu C is defined by this equation. And here, this EI star is generator of T star. And, I've used that it's a complexified basis. This is called the hyperkähler moment map. And this can be defined by the if this generally if this G acts on HM which preserves hyperkähler structures, then we can define this kind of maps. And especially from the torus actions, we can define hyperkähler moment map like this rule. And from this moment map, we can define the hypertoric. And, a hypertoric is defined by like this. You take a non-zero alpha from K star. K star is this part. Then, by definition, this element becomes a regular value of this hyperkähler moment map. So we see that it's a regular value because of regular value. This pullback mu HK inverse alpha 0.
Complexification of T star, that's a tensor product with C, right?
Yes, yes.
So you are considering.
Okay. If you have any questions, please ask me. And so yes, this is a regular value. So this mu HK inverse alpha 0, mu HK inverse alpha 0 is lived in this space, has a almost free.
I'm sorry, how does this question? What is K? K is any group or?
Yes, any arbitrary subgroup.
Arbitrary closed subgroup?
Yes.
Or you are only considering torus?
Yes, in this case, because it's a TM, its subgroup is always
Lisa
torus.
Connected Lisa group?
Yes, this subgroup.
There are some discrete groups, subgroups.
Connected. And it's almost free K action. So almost free means its isomorphic subgroup is a finite for all x. And so we see that its orbit quotient space is becomes orbifold. And it has a Tm over K action.
Is it clear that this mu HK defined this way, this is K invariant? Seems to
K
be, right?
invariant, yes, right.
This K invariant.
Yes. Yeah. Because K action K star is trivially.
So, I mean, the value of KR is okay, but MC. Oh, so
because
that's
it's
why you want to just take inverse image of alpha and 0, right?
Yeah.
Should it be called Sugar-free or
Almost
almost free?
free.
It's sugar-free. Sugar-free is
Oh, I've never had sugar free.
no, sugar-free is a proper word.
Oh, really?
Yeah.
I've never had that.
Isotropic circle is circle fixed, I think torus or circle.
Mm-hmm.
Maybe circle. Isotropic circle is finite. There seems to be. I mean, sugar-free action is.
It's the same definition. So from this one, we said this space is a hypertoric variety. We say is and
Are you also assuming that T to the M quotient K is also a torus?
yes, because K's are connected, so it becomes torus.
If you had taken, let's say, double covering, then you still
In that case, you have some finite part. Yes. Because K's are connected, so it's connected to us. Dimension of this space is like this. So first of all, this lives in this space, and HM is has a dimension 4m, and from minus and mu HK inverse alpha 0 is a pullback of the regular value. So this first part has a dimension of this one. And divided by k, so finally you also minus dimension k. So we see that this manifold has 4 times dimensions of m minus dimension k. And therefore, if we put this dimension, okay, is n. This is this part. Then this dimension is it's 4n. Therefore, hypertoric variety is a class in a is the class in M4n Tn. So it's a little bit different as a toric manifold. In a usually toric manifold case, it becomes 2n, but hypertoric is always 4n. So for example, the next example is a very typical example in a hypertoric variety. For example, you take this subgroup from Tn plus 1. And now Tn plus 1 acts on n plus 1.
You have this specific construction. I mean, you have a hypertoric manifold coming from Quaternion space, and you construct specifically this hyperkähler moment map, and you take a regular Fourier inverse image and quotient with k. Seems to be there are not many choice, but only depending on alpha. Is this the whole definition of hypertoric? Hypertoric always comes from that, or that's the example?
If you take the, you can take this part is better. If it's a regular value, so it's a whole definition of the hypertoric manifold.
So depending on the choice of these regular values, you get all different hypertoric varieties.
Yes. After that, I will talk about that. Actually speaking, its diffeomorphism type is not dependent on the choice of this regular value.
My question is, then you only have one hypertoric manifold.
What? It's dependent on embeddings of the k.
Embedding?
Yes.
Oh, depending on k.
Yeah.
K.
Yes.
Okay, so embedding.
Yes. And this determines some geometric structure, complex structure, or hyperkähler structure, or something.
The embedding of subtorus k into Tn.
Yeah.
So the hypertoric manifold, there are as many hypertoric manifold as the embedding of k.
Yes.
And this alpha is a continuous parameter?
This alpha, yes, continuous parameter.
It's a deformation?
Yes, right. So that's the reason why all of them are diffeomorphic.
So the reason why you take t plus t to the complexification and t, and you have moment map mu r plus mu c, that's to make this one into 4n dimensional in Tn.
Yes. Right. Actually, it's a more general strategy. It's defined by the Hitching as a hyperkähler quotient.
And what happens if you just sending map from Hm to just T star?
Just T star.
Forgetting about tensor part.
It's the same symplectic reductions.
That's symplectic reduction.
Yeah.
How about compactness?
It's not fold. It's always non-compact.
Always non-compact.
Yes. And for example, this is a very typical example. Then we get divided by delta. It becomes a cotangent bundle of the CPN. So it's a non-compact. So where? Is induced by CPN. So finally, in this section, I will give some property on a main theorem. One of the properties that, as I said, its diffeomorphic type is doesn't depend on the alpha. This is proved by Bielowski dancer. You take two different alpha and so it's really then these two hyperkähler manifold is a different. If you take different alpha and alpha prime, and if k-axon are freely on these two parts, these two products, then these two hypertoric variety is equivalently diffeomorphic. T is a Tn.
This is a TN, TN diffeomorphism.
Yeah, Tn diffeomorphism. So in this seminar,
Is there any necessary sufficient condition for this embedding K so that this action is free?
yes, I will explain after that. Actually, it's almost same as a toric case. The main theorem. What I want to talk in this seminar is if you give two hypertoric manifolds, and we assume this two equivalent cohomology is same as an stability algebra, then the two hypertoric varieties are equivalently diffeomorphic. This is today's main theorem. And hypertoric is a hyperkähler analog of the toric manifold. And in the toric case, in this case, Masuda proved the above type of theorem. This is finished introductions. So in the next section, I want to talk about equivalent cohomology and hyperplane arrangement. Hyperplane arrangement is defined from the hypertoric variety. Yes, it's a hyperplane arrangement. Yeah. So yeah, I will talk about it. So first of all, I will define the equivalent cohomology quickly. As I said, equivalent cohomology is invariant of the group actions. So first we need some group actions. Let T axon M. T is an arbitrary group. Especially in this talk, T takes a torus. And it is the space called the universal space of the universal space of T. It satisfies this space is contractible and T acts on this space freely. Then we can construct this kind of space, Et times M. So we take M. M has T actions, and also Et has T actions. So we can define the diagonal T actions on this space. Then now Et has free T actions, so this action becomes freely. Then we can take this kind of space here. This is only the orbit quotient space from these actions. Then this space has some nice bundle structures. That is, this has a base space as Pt. Pt is Et divided T. And its fiber is M. So Et times M over T has this kind of nice fiber bundle structures. And equivalent cohomology is just take the ordinary cohomology of this space. So we say this cohomology and equivariant cohomology. Of T and T. And we often call this space as T star M. Now remark. This HT star M is not only a ring structure, but also has a H star BT algebra structure from this fiber bundle structure. So this H star BT algebra by this map. We denote this projection as pi. Then we take its induced homomorphism. Then we have this map. So from this map, we can regard HT star M as the H star BT algebra. So it's an explanation of the given cohomology. And next I will explain about the hyperplane arrangement. It's associated from the hypertoric manifold. In this section, I will talk about if you give some hypertoric manifold, then it determines some hyperplane arrangement. Which is in Tn star. Now, yes, I will write this maps. Now we see this map, and we denote it. This inclusion is iota, and this row is it's a cokernel of this part. And from this map, from this Lie group maps, Lie group homomorphism, we can associate the Lie algebra homomorphism. And here is T. And here is star Tn. And it's exact. And from this Lie algebra homomorphism, we are associated a dual of Lie algebra homomorphism like this. What's that? And it's alpha is lived here. This alpha determines hypertoric manifold because we take some pullback of the alpha 0 and divide by this k. And this is now it's a surjective, so there is some rift here. Alpha chilled up. Alpha chilled up goes to alpha, this alpha, and now it's determined. Hypertoric. That is this M4N. M4N, I'm sorry. Yon is Japanese. It's M4N is denoted by this one. This alpha is here, lived here. And from this alpha tilde, we can determine the hyperplane like this. We denote the first hyperplane is HI. HI is a subset of the here, Tn star is here, and which satisfies this one. Here, this EI is a canonical basis of the it's a basis. It's in T. Yes. Yeah. Now U is lived in here, and rho star U is here, and now HI is determined by rho star U plus alpha tilde, and Equivariant is EI. EI is a basis of T here. Then it is 0. From this space, we can determine some hyperplane in a in a Tn, and we take this set from H1 to Hm because now T has m basis, so we can take equal 1 to n. And H alpha is here. So this kind of hyperplane arrangement structure is determined from alpha. And we denote this set as H alpha. And we call it this H alpha. So U is the element in here. And rho star U is here.
So why is HI hyperplane?
HI is hyperplane. It's yes, codimension 1. Because in usual case, if this doesn't appear, then it becomes some
Subspace?
yes. And EI part is 0. So we have some one-dimensional normal vectors we determine. And yes. So this gives some.
Alpha, for each alpha, yeah, okay, yeah, right.
For each alpha.
No, for each I, you have HI. I was confused. Okay.
Oh, yes, yes.
So that's a hyperplane.
Yes, HI is hyperplane.
Is there some special property about this hyperplane arrangement? Like, are they non-degenerate or?
Yes, yes. I will explain later. And this called a hyperplane arrangement associated from hypertoric manifold. Yes, M hyperplanes. M is a dimension of T. And for N is this hypertoric. And for example, as previously, I give this example. T star CPN becomes one of the hypertoric. And if we take n equal 2, then it also a hypertoric manifold, a dimensional hypertoric manifold. And now,
What about choice of
Alpha tilde.
alpha tilde. It's some as I said, it's if you take another alpha tilde, then this gives some parallel moving. Yes. So it's only changed some positions, only parallel positions. So it doesn't change the combinatorial structure. This T star CP2 is determined from this one. We take some diagonal element, diagonal subgroup from T3, and it's a Lie algebra is R itself. And so we take some element from here, not 0. And so yes. We can easily to see that this map gives this kind of map. Proceed. So you take this element from T3 star, ABC. ABC is in A is R, and B is C is also R. And this goes to A plus B plus C. This is this map. Then, for example, if you take R equals 3 as a non-zero element, then it's alpha tilde we can take, for example, 1, 1, 1. This is alpha tilde. And also from these definitions, we see that this roster is this kind of map. And let's determine the this H1. H1 is a set like this. You take element from T2, and this element satisfies this one. First of all, it's a roster U plus alpha tilde plus alpha tilde is this one. 1, 1, 1. E1. 0. So we see that this one is like this. T1, T2, and equal -1. you can easily check that because rho star U is defined by this one. So we can take T1, T2 minus T1 minus T2. And this must be 1, 1, E1 is 1. Yes, 1. So this must be. So okay, I will write it. Yes. This part becomes this one. T1 plus. It's okay. Yeah, maybe there's no problem, I think. Plus 1 and
So H2 is also
E1. Yes, right. So yes. This becomes 0. So it must be T1 plus 1, must be minus 1. So yes, as Professor Sa said, H2 is T1, T2, and T2 is minus 1, and H3 is T1, T2, T1 plus T2 is minus 1. So its hyperplane arrangement is like this. T1, T2 is yes, it's 1. Yeah. Thank you. So its hyperplane arrangement is something like this. T1, T2, and this is T2 star. This is also to the two-dimensional plane. And now H1 is this part. H1 is all of them. All of T1 is minus 1. So this one is H1. Now H2 is all T2 is minus 1. Here minus 1. And H3 is T1 plus T2 is 1. So in this case, maybe here. Maybe it's 1, 1. It's 1, 1, I think. This kind of. So we can determine from T star CP2 this kind of hyperplane arrangement in T2 star.
it looks like when you consider the CP2, and then CP2 gives you polytope,
Yes.
and then polytope gives you the hyperplane range.
Yes.
Is it always true?
Yes, it's always true. So yeah, actually in hypertoric, some toric is embedded in the hypertoric manifold. So in this case, it's CP2 is embedded in this CP2, and it's appeared in this range. This one. This corresponds to the polytope of the CP2. So I will give some facts about manifold. It's only 10 minutes. I'm sorry, I need to speed up. It's yes, it's as I said, its combinatorial structure. It doesn't depend on the choice of alpha filter. Non-alpha filter. It's only parallel movings, and yes. You give some hyperplane arrangement, Tn star. Then we can determine the hypertoric manifold. So this previous explanation is this directions, but this direction is false. But this hyperplane satisfies the simple. In this case, always we can determine the hypertoric manifold. Simple means yes, this one. You take the intersections of the hyperplanes. It's non-empty, and this I is coming from the subset of the M. Then its dimension is always n minus the cardinality of I. So for example, these two H1 and H2 is this kind of how do I say this kind of things. If two hyperplanes is doesn't intersection, this kind of thing, that is H1 and H2 is same hyperplane. In this case, this doesn't give the hypertoric manifold.
In other words, the bounded regions are simply free.
Yes, right. And yes, when hypertoric becomes a hyperplane manifold, we also determined by the structure of the hyperplane arrangement. Now, the n hyperplanes is intersect. So it means that from these conditions, this is a one point intersection of n hyperplanes. Then this rho star EI forms Z basis of the lattices on Tn. Then hypertoric becomes is a manifold. So rho star EI is this one. Rho star is this map. And EI is a basis of this element. And this rho star EI forms a Z basis. Then it becomes a manifold.
In other words, the action is action of K.
It's free. Yes. Okay. And okay, and I will introduce this basic theorem. It's proved by Kono. It's the same year as the Kuroki tensor. This equivalent cohomology ring is the same as the Stanley-Reisner ring of the hyperplane arrangement. Where M is a hypertoric manifold. And this tau is degree is 2. So for example, in this hyperplane case, it corresponds to T star CP2. From his theorem, we see that this equivalent cohomology is we need to numbering. this hyperplane. Then this equivalent cohomology is like this: tau 1, tau 2, tau 3. These correspond to the hyperplanes, the number of the hyperplanes, and it's divided by the ideal, which is satisfies this one. So in this case, it means that if the intersections of the hyperplane is empty, then this multiplication is generated this ideal. So in this case, for example, H1, H2 is there is some intersections. So H1, H2, tau 1, tau 2 doesn't generate this ideal. But tau 1, tau 2, and tau 3, H1, H2, H3, its intersection is empty. So this ideal is generated by tau 1, tau 2, tau 3. So it's known from the Konno's theorem. And my idea to prove the equivalent cohomology determines hypertoric manifold. To prove it, I will construct the hyperplane arrangement from the equivalent cohomology, because a hyperplane arrangement and hypertoric is 1-to-1. So to prove the my main theorem, first of all, we see the this sequence. Start here. Star, K star. And from here, we see that, and we take some element. We have some hyperplane arrangement. It's in Tn star. And from here, we see that we can construct the hypertoric. From here, we see we have some equivalent cohomology. And from Konno's theorem, we also have some, this sequence in the second degree part, H2BT. This is coming from the projections of the hyperbundle. It's equivalent cohomology, and it's to them. So we take from this sequence, and the element of here, we have another hyperplane arrangement. And what I proved is this H alpha and H beta has the same combinatory structure. So it means that from the equivalent cohomology, we can construct the hypertoric varieties. So this is that these directions. I have no time, so I will talk. I will explain. I will give some statement of the main theorem. So the main theorem is section 3. The main theorem is this one is main theorem. As a PT algebra. Then we see that if we denote this is F, and we can define some a hyperplane from here. And now alpha is to m. And this hyperplane and from this H star PT algebra, we can associate this isomorphism. I will abuse F and F. And from this F alpha, we can determine another hyperplane arrangement. And these two hyperplane arrangements are same in H2BT. This is my main theorem. So as a corollary of this theorem, from the two equivalent cohomology, we have the same hyperplane arrangement. So as a corollary, if these two equivalent cohomology is isomorphic as the H star BT algebra, then
this hypertoric manifold, hypertoric. If you have a toric manifold, can you always find a hypertoric manifold containing